So we saw in the previous class up to initial distribution, a small correction on the state space. The spectrum of these xi's, x1, x2, x1 are stochastic process, means sequence of random variables. The sequence of random variable. Spec X is a subset of the state space. So you can think the state space as a union of all spectra. So in previous class, we defined what is random walk, what is stochastic process, random walk over Z actually, over Z. Z is the state space, and we also find a distribution, conditional distribution, not the joint distribution or not the marginal distribution. Then we define transition function, Pxy is equal to probability of xn plus 1 equal to y, xn equal to x. That means from state, if it is state space, S is the state space, there is x, from going x to y, the probability is x. Now this does not depends on n, does not depend on n. It may depends on n, but if it does not depends on n, then it's called stationary stochastic process. So it's a Markov chain. Is a Markov chain is a discrete time also discrete, because the time is 1, 2, 3, 4 suffix are discrete, and this state space also discrete. State space may be finite, may be infinite, but time index, it is infinite, all natural number union 0. So xt, but t belongs to natural number union. This is stochastic process, the collection of all random variables. Then we define a function p suffix xy for a fixed x. If you fixed x, from x you can go some y1, you can go y2, you can go x also, from x to x. This should be a PMF, because once we in the x, the probability of transit to the other state, the sum must be 1, because it's a conditional probability. So in conditional probability, this is PMF. So if say f is a PMF, f of xi, the probability of x equal to xi, which is a PMF, then this implies the probability of x equal to xi given under something, some x belongs to or some any other event, this also PMF. You can easily check that is also PMF. Homework. So probability of x equal to xi, if it is a PMF, then probability of x equal to xi given a also PMF. It's not only PMF, it is a density function, then also some given under conditional, it's called conditional density. It's also PMF. Then we should define initial distribution. What is initial distribution? Starting distribution, that is pi 0 x is equal to probability of x0 is equal to x for all x belongs to the state space. This is not only for random walk, not only for Markov chain. This definition is for any discrete time and discrete. This also maybe the state space may be continuous. Then this will be density, then initial density, but it should be time space should be discrete. The next challenge is to find the joint distribution. So this by definition we can easily find this conditional probability, because the conditional probability by definition, the conditional probability, we know what is the conditional probability by definition. But joint distribution, this is a challenge to find joint distribution. How to find joint distribution? Say we want to find joint distribution of x0 and x1. So what will be that? The probability of x0 equal to x0, x1 equal to x1. What is this? This should be sum over. Oh no, not sum over. Sorry, not marginal. It is probability conditional probability x1 equal to x1 given x0 equal to x0 into probability of x0, x0 equal to x0. So this is just a definition of conditional probability. Now this is just p x0 transition function, transition probability from x0 to x1, and this is pi 0 x0. So this is the joint distribution. Now what will be the joint distribution of 3? We know this is probability of x2 given is equal to x2 given y1 is equal to x1 equal to x1, x0 equal to x0. This is a multiplication rule. Then probability of x1 equal to x1 given x0 equal to x0 into probability of x0 equal to x0. Now by Markov, this is a Markov chain. So now we are using the Markov chain property. This is for any general random variable, tree random variable. Now here we are using the property of Markov chain. By Markov chain property, this is x2 is equal to x2 given x1 equal to x1, probability of x1 equal to x1 given x0 equal to x0, and probability of into probability of x0 is equal to x0. Now what is this? This is pi 0 of x0 starting initially, then the probability of going x0 to x1, this is the second middle one, and this is the leftmost one. Is we know this is not depends on n. So x2 equal to x2 given x1 equal to x1 is same as x1 equal to x1 given x0 equal to x1. Probability of x2 equal to x2 given x1 equal to x1 is same as probability of x1 is equal to x2 given x0 is equal to x1. So it does not depend on this index 2 and 1, but this obviously depends on the small x2 and small x1. So this is smallest x1 to small x2. This is the, and we can easily show by induction is homework again. So by induction, you can easily show that the joint distribution of x0 is equal to x0, x1 is equal to x1, xn is equal to xn is nothing but the initially start from x0, then from x0 to x1, this transition probability, then x1 to x2, again the transition probability, and up to xn minus 1 to xn, the last one. Now question, maybe conditional probability may not be defined. Maybe so happen this conditional probability not defined. Then what happens? If conditional probability does not define, is assuming that all the conditional probability is defined. Because maybe x1 equal to x1, the probability of x1 equal to x1 may be 0. So in that case, this is not defined. Conditional probability. What happens? If conditional probability is not defined. Easy. Just we define as 0. No need of going in probability, conditional probability. So we want to find probability of x0 equal to x0, x1 equal to small x1, and capital X2 random variable is equal to small x2, where the probability of x1 equal to x1 is 0. Now in that case, the transition probability from x1 to x2 is not defined, because from x1 to x2 is just probability of xn n plus 1 is equal to x2 given xn equal to x1. And this is not defined. So in that case, we just define that probability as 0, joint distribution as 0. So no problem. If something is conditional probability is not defined, that means the denominator is 0. In that case, we define the probability of x0 equal to x1, x1 equal x0 equal to x0, x1 equal to x1, x2 equal to x2 as 0. If any one of them is 0, we define this, define is 0 if one of them, if one of them this is 0 for at least one I. At least one I. If for at least one I this is 0, then we define I from 1 to n. If at least one I this is 0, then we define this as 0, because it's a subset of this. X equal to x, y equal to y, this is a subset of x equal to x. So then we should not define like that, because then the transition probability from xi to xi plus 1, that is p of xi x comma xi plus 1, this is not defined. In that case, we define this as 0, obvious way. So there will be no problem to define joint distribution even if the conditional is undefined. We define directly. Now there is a fact, important fact. Given any transition function, now if there is a Markov chain, we can find the random walk is a easy example of Markov chain. Consider random walk, say. For simplicity, take random walk or any other Markov chain. Given a Markov chain or a random walk, we can easily find the transition probability. That is easy. For random walk, it is very easy. So probability of transition probability from x to x plus 1 is p, x to x minus 1 is 1 minus p, and any other x to any y, where y is not x plus 1 or x minus 1 for random walk, it is 0. So it can go one step forward from x to x plus 1, it can go one step backward from x to x minus 1, no other step. Now the question is the other way. If I have a transition function, no Markov chain, nothing, no random variable, I give a transition function. I give you a transition function p of xy, I give you a function pxy, say, for a fixed x. For every x, I give a PMF. For every x, I give you a PMF pxy. For a fixed x, px is a PMF. I give a set of PMF. So state space is say 0, 1, 2, 3. I give you a 4 PMF. P0y, P1y, P2y, P3y. So can you find a Markov chain? Is there any Markov chain whose transition probability is same as this transition probability? These are other way question. If I have a Markov chain, I can find the transition function. If I give a function which is transition function, is it a transition function of some Markov chain? This is a question. So this same question arises in probability also. If there is a random variable, we have a distribution function, and then we have a density function. In this case, there is a PM, or there is a moment generating function, or there is a cashes function. The question is the other way. If I give a generating function, there is some condition. I give a function such that the sum is 1 and this all are greater than or equal to 0. Then can you define a random variable for which random variable this is a PM? The same question is here. Given any transition function P and any initial distribution, you have to give initial distribution also. Any initial distribution. What is initial distribution? It's just a PMF. It's nothing, not coming from the Markov chain. I give you a just PMF. I give you a say binomial. So all the pi 0 xi is greater than or equal to 0, and sum over all xi pi 0 xi is 1. So I give a initial distribution. Is there is a random variable stochastic process? Yes, there is a. The answer is yes. There is a probability space. There should be a probability space. Otherwise, you can't define a random variable. Probability space and some random variables. Xn n greater than or equal to 0, such that what happened? Such that this probability, the joint distribution of this, is actually the given pi 0, the given distributions, product of this all. So that means your right hand side is given to you first. What is the difference between previous and this one? Previous, we know the left side, and then we know this is the equal. And now it is P, the all capital P is given to you. This side, oh, by the way, this P and this P are different. These two P are different, remember, because this is a probability P. And this is a function. This is not the probability. This is a function, remember. Because if it is a probability, then some random value should be there, or maybe some event. But there is no event. The P of some 0, 2. It's nothing event. No event is there. So this P is not probability. If I say P of 0, 1, so this P is not probability. So this is same as probability of x1 equal to 1 given x0 equal to 0. Now this P is a probability P. So now this right hand P, the transition function P, this is not the probability. If it given to you, we can find that probabilities using this formula. And if you give the probability first, you can find the transition function there second. Then, so both ways possible. And this random variables comes a Markov chain. You can easily check. Now we prove it. Now homework is this, by induction we can prove it. Now the other way. If this is given to you, the last line, this is the last line. what we prove here. We assume this actually here. We assume that probability of x to this one. Actually, this is the properties of Markov chain. We use the Markov chain here. So using this, we prove the last line. Now the other way, if the last line is given to you, you have to prove this implication, this Markov chain property. Now you can't use the Markov chain property now. I will give you this. This is the given to you. This line is given to you. So from that you have to prove. So it is again is a homework that probability of any xi plus 1 equal to y given xi equal to x is same as probability of sorry xi minus this xi equal to I say, or say it is x xi minus 1 equal to xi minus 1 x0 equal to x0. This is probability of xi plus 1 equal to y given xi equal to x. So you have to prove it now. So using this, you can prove this that the previous line, and using the previous line, you can prove this. So this is again the homework, and this x1, x2, xn's are this sequence is the Markov chain. So once you prove it, we know this is a Markov chain. And this Markov chain having the same transition function that p, this p, and the initial distribution pi 0. So now you have to prove that this Markov chain has this initial distribution pi 0. Again, this is again one more homework. So this is a Markov chain with this transition function p. That p is not the probability p. This is the right hand side p, and initial distribution pi 0. So do you realize the difference? In first, we define Markov chain like that. So we have a probability, and we have a probability space. We have random variables. We have a probability, and then we have a initial distribution, and from that we can find the joint distribution. Now the question is the other way. We don't know any random variables. We don't know any probability space. We don't have any Markov chain, such a thing. We don't have random variable at all. We have only a function p, which is a transition function. Nothing we have. From that p, we know p. We know only p01, p02. That value we know. p03, then p00. Then we know p10, p1. This p is not probability. It's a transition function. Is a function. We have to prove that this is a transition function from some random variables, sequence of random variables, which follows the Markov chain. That means what? That means you have to construct the random variables. Two different ways. So the one way thing I give you, I told you that these are the random variables. This random variables has this property, probability, this. Find the transition probability. This is one question. Another question, I'll give you, okay, this is a function. Say probability of p of 0, 0 is say half, p of 0, 1 is say 0.3, p of 0, 2 is say 0.2, p of 1, 0 is say 0.5, p of 1, 1 is 0.4, and p of 1, 2 is say 0.1, and p of 2, 0 is say 0.8, p of 2, 1 is 0.1, and p of 2, 2 is 0.1. Now find a sequence of random variables. This is a question. You have to find the random variable now. So sequence, the stochastic process. You have to find the probability space. You have to find this where the random variables are defined, where the state space, everything you have to find. And you have to find the random sequence of random variables. What are the probabilities of these random variables such that this random variables forms a Markov chain, and that Markov chain, if you find the transition function of this Markov chain, that Markov chain that will match with this given function. So in problem set, I'll give one problem on that. I precisely describe this the p function, and then I ask you to find the random variables. So this is a more important fact. Now state space of the Markov chain. So I already told you the state space of the Markov chain is this is union of all the spec of xn, and if it is a continuous state space, for continuous state space, that is not continuous. Maybe Markov chain may be continuous state space. Some probability may be 0, right? The probability distribution is discrete, but space may be continuous. So you can say the whole state space is real number. The state space is a real number, but the distribution may be finite, maybe discrete. I say from 0 to 1, it is say half. 0 to minus 1 is half. From root 2 to root 2 plus 1 is half. From root 2 to root 2 minus 1 is half. We can define such a way. Maybe the state space is continuous, but still need a Markov chain. Maybe your state space is continuous, but the time index is discrete, and the spectrum is maybe finite. Here is 2. For randomly, every spectrum has only 2 elements, x plus 1 and x minus 1. No. Sorry. It is not a 2. For x0, for x1 it is 2. For x2 it is 3. It will increase. From x2 it is from 0 you can go to the minus 1 and 1. Then the next step you can go to the 0, 2 and minus 2. So x2 it is 3, x3 it is 4, for xn it is n plus 1, right? But it is finite. Your state spectrum is finite, but this maybe your state space is continuous. In that case, again, what is the state space? Your state space will be union over all this, because now this n is 1 to infinity, because n is natural number, because this n is actually indexing. There's 3 things. One is this indexing thing, that index xn, xi, this index. This may be discrete. This may be sequence. That means the natural number. This can't be finite, because it is, since the sequence of random variables, it can't be finite. This may be continuous. In later we see this is called Markov jump process or Brownian motions, and there this index may be continuous. Next one is the spectrum of every random variable. This may be finite, maybe infinite, discrete, continuous, and then one thing is the state space. So you have to clearly understand what are the state space, what are the spectrum of this each random variable, and what is the indexing parameter. And many times it is a time, actually, this indexing parameter. In time series, also there is a stochastic process with the indexing parameter is time. Now the continuous space is just support. It's called support. Then for continuous we don't say spec, we say support. So what is spec? The spectrum of x is for discrete case. For discrete case, discrete means the discrete instance of the output of the random variable, not the discrete instance of index. That for the random variable discrete, random variables are discrete. What is this? This is set of all x such that the probability of x equal to x is positive. This is the spectrum. And what is the definition of support? In continuous case, We don't say as a spec. Continuous case, we say the support of x is set of all x such that by the density function, this is a density function. So f is a density function. Density function. So density function is positive. So for normality, support is the whole R. For uniform 0 to 1, the support is 0 to 1. So otherwise, it is 0. The density function is 0. Because we can't define like that for all x, set of all x as that probability of x equal to positive. Because for continuous case, for every small x, the probability of x equal to x is 0. So this is support. Now finite, for finite state space, it is finite high state space. We take this as a 0, 1, 2 up to d. D is some natural number. D may be 1, D may be 1, only 2, 0 and 1. And you can consider the subset of Z also. So note, there is a note for a stochastic process. This or somewhere we can write this also like that also. Anyone you can notation you can use. The right hand notation is a more precise notation, set theory notation, and some author also write in the left hand side notation also. There are two underline set important. There are two underline sets. One is called index set T, and another is one state space. Now we consider now for random walk and for now Markov chain is both are discrete, but in Markov pure jump process there may be state space may be continuous, but we do not consider the case আমরা আপাতত বাদ দিচ্ছি এটা consider the case when T is continuous but state space is finite discrete. So this is a more complicated, most complicated thing. Your state space is discrete, but your time is continuous. But your state space is discrete. What is the meaning? This is called Markov pure jump. The last of the syllabus, I maybe give some one or two talk on that. The state space is discrete, but time is continuous. What is the meaning? Meaning, there's some say there are four in state space. There are 0, 1, 2, 3, 4. So we start from the 0 and we stop there for some time. May not, we don't know how many times. Maybe 1 hour, maybe 1.2 hour, maybe 1.3947810 hours, maybe pi hours, maybe e to the power pi hours, any real number, and then jump from 0 to 1. Again, stay there for some time. That means your time is continuous. Your ingression parameter is continuous, but where it will go, that particle, that is discrete and finite in this case. Maybe both continuous, yes, they move both continuous like a Brownian motion. A particle is there, it is moved around, it go anywhere from in the space. Both are continuous. Both are discrete, yes, both are discrete. Is like a this Markov chain, like a machine. Today fail, tomorrow it may fail or maybe in a working state. after 1 hour. Can the other way the time is discrete, a state is continuous? Then what is the meaning of that? So that means a particle jump after some unit of time, start from 0, say. It can't jump after 0.2 second. It have to jump either after 1 second, or maybe 2 second, or maybe 3 second, discrete time. But it may jump anywhere. From 0 it can jump to the 0.3, 0.4, minus 0.7. So in Markov chain, we do not consider that T is continuous, but state space is discrete. There is some example, good example is soccer. Soccer is a good example for that. T is continuous, but state space is finite. In soccer, the whole 90 minutes is the state space, and the event occur, that means a goal occur, that is finite, finite and discrete. So for say team A, the starting as time 0, the goal is 0. That first goal may occur at any time. So it is a time is now continuous. But that goal, number of goal cannot be 0.3 or 1.9. That your state space is 0, 1, 2, 3, 4. Now in Markov chain, we do not consider this case. This is called Markov process, we will consider later. Now there is one example of Markov chain is this. This example 2, Markov chain with only 2 steps. Easiest having 2 steps. Only 2 steps. Working state and in non-working states, 0 or 1. So state space is only 0, 1. Say 0 for is working, 1 for is not working. So it is a machine, say there is a machine. It's only 2 steps for a machine. Real life example is a machine in the working state and non-functioning or non-working state. Functioning or non-functioning state. So it is working state is 1, non-functioning 0. Now we can easily, we have to define 4 probabilities from working to non-working, non-working to working, working to working, and non-working to non-working. The next day, here time is unit time, so it is a next day or maybe next hour after 1 hour. We assume there is nothing called say 0.3 hours. If it is non-working now, it is after 1 hour it is work. We will assume that probability, not that probability after half hour what will happen. It is working or not. We always consider that after 1 hour. So that means say if it is non-working, the time, at least the time for it is correcting is say 1 hour or maybe 1 day. What? So there are 4 probabilities, and you can actually see this is actually 2 probabilities. So you know from working to non-working that you can find the 1 minus that is the working to working. So this 2 probability you can find a graph of that is called graph. The graph is not a function. Graph of function is a Euler graph theory. Euler devised this graph. So there's 2 states 0 to 0 and 1, and you can go from 0 to 1. If it is non-working to working, it's a probability P, and if it is working, then the next day it will be non-functioning, which is Q. Obviously, P plus Q not equal to 1. Maybe 1, but may not be 1. So for non-working to working, it is a with probability very high probability 0.9. Say. If it is non-working, then next day is working is 0.9. And from working to next day non-working, it will be very low, say 0.001. So obviously from 1 to 1, it is 1 minus Q. And obviously from 0 to 0, it is 1 minus P. Remember, this 1 minus p is not q. So this diagram actually clearly visualize what is the Markov chain. This diagram is enough for this Markov chain. This is called graph representation of the Markov chain. So n probability of xn plus 1 is 1 given that xn equal to 0 is p. Probability of xn plus 1 0 given that xn equal to 1 is q. So you can easily find probability of xn plus 1 equal to 0 when xn equal to 0 is 1 minus p. If we add these two, this will give 1. Probability of xn plus 1 equal to 1 given that xn equal to 1 is 1 minus p. Remember, for a fixed given thing, fixed xn equal to 0, this is sum is 1. But for a fixed y, that is this, adding this and this not equal to 1. So given xn plus 1 equal probability of xn plus 1 equal to 1 given x0 plus probability of xn equal to xn plus 1 equal to 1 given x1, that sum is not 1. This is 1 plus p minus q. That may be 0, that may be 2. Obviously, this is from 0 to 2. So obviously, this is probability, so it can't be go beyond 2, can't be negative. Now we have a say initial distribution. So initial distribution means you have two values, only pi 0 of 0 and pi 0 of 1. Start from 0, initially start from 0 and initially start from 1. So this four quantity basically p, q and pi 0, pi 1, pi 0, 0 and pi 0, 1, this describe whole the procedure. So then what will be the probability of this x1 is equal to 0? That is nothing but probability of x1 equal to 0, x0 is equal to 0 plus probability of x0 equal to 0, x1 equal to 0 and x0 equal to 1. Now what is this? This is probability of x1 equal to 0 given x0 equal to 0 into probability of x0 equal to 0, x0 plus, oh sorry, this probability of x0 equal to 0. And probability of x1 is equal to 0 given that x0 equal to 1 into probability of x0 is equal to 1. Now what is this? This is, we know this is just transition from 0 to 0, 0 to 0 is just 1 minus p. So it is 1 minus p pi 0 0. Oh, by the way, actually you need 3 quantity, not the 4 quantity. P, q and this pi 0 0 is enough because pi 0 0 plus pi 0 1 is 1 and both these are greater than 0. Maybe 0, if it is 0 this is nothing. If it's starting it is initially it is non-working, yeah, maybe 0. Maybe it is starting it is say working. So pi 0 0 is 0. That may be 0. So it's need only 3, small p, small q and this pi 0 0. So this pi 0 0 plus, what is this? This is q. What is that? That is 1 minus pi 0 0. This is pi 0 1, so it is 1 minus pi 0 0. That means it is 1 minus p minus q pi 0 0 plus q. This is the marginal of x1 is equal to 0. And what is will be the probability of x1 equal to 1? This is nothing but 1 minus pi x0 x1 equal to 1. This is just 1 minus this value. Sorry, pi 1 equal to 0. X1 equal to 0. So we have this marginal distribution of x1. So we can find marginal distribution of xm also, and you can easily check that this probability of xn plus 1 is equal to 0 is nothing but probability of same thing. Probability of xn plus 1 is equal to 0 and xn is equal to 0 plus probability of xn plus 1 equal to 0 and xn equal to 1. Now this is again probability of xn plus 1 equal to 0 given xn equal to 0 and into probability of xn equal to 0 plus probability of xn plus 1 is equal to 0 given xn equal to 1 into probability of xn equal to 1. Now this we know, this is just same as this. It is 1 minus p, and this is probability of xn equal to 0. This is not pi 0, and this is q of probability of xn equal to 1. So this is a probability. Now you can easily find this is nothing but 1 minus p minus q. This is probability of xn plus 1 is just 1 minus probability of xn equal to 0. So it is xn equal to 0 plus q. Now it is homework. By induction, you can prove that. You can easily prove that probability of xn plus 1 or xn is equal to 0 is nothing but 1 minus p minus q whole to the power n pi 0 0. So it's clear what you have to do. You have to replace that probability of xn equal to 0 in terms of probability of xn minus 1 equal to 0. And again there will be this term 1 minus p minus q, again 1 minus, so whole to the power n will be there, plus q into somewhere j equal to 0 to n minus 1, 1 minus p minus q whole to the power j. This will be the marginal distribution. Why I calling margin distribution? Because if you know probability of xn equal to 0, you can easily find probability of xn equal to 1. So there are only two steps, 0 and 1, so this distribution is given to you. So probability of xn equal to 0 is this. Now some trivial case. P, Q are both 0. What is the meaning? That means P, Q 0 means if you start from working state is always in the working state. Start from the non-working state, always in the non-working state. Transition probability is 0 for every two state. So this is then clearly probability of xn equal to 0 will be pi 0 0. If start from pi 0, then again the same probability will be to remain 0 for every n, and pi probability of xn equal to 1 is the pi 0. So non-interesting case. It's actually nothing. Not a. It's a Markov chain. It's a stochastic process, but this is a trivial thing. If the other way, if p equal to 1, then q and q equal to 1, that means every day if it is non-working, then next day it is working. Again next day it is non-working. Next day it is working. This again is a non-interesting case. So interesting case is where? So we assume that p plus q is positive. So both 0 is a non-interesting case. And in that case, what happens? In that case, probability of xn equal to 0 will be what? Now we have to add this. This is a GP sum, the geometric progression. J equal to 0 to n minus 1, 1 minus p minus q to the GP sum. And if we add this, is again homework. You can check that this is, take the GP sum and calculate. You will get q by p plus q plus 1 minus p minus q whole to the power n, and this will be pi 0 0 minus q minus p plus q. And your pi probability of xn equal to 1 is, it is just replaced by q replaced by p, and q replaced by p, and p replaced by q. So 1 minus p minus q whole to the power n to pi 0 1. Basically, if we change the name 0 to 1 and 1 to 0 and p to q, q to p, it will be the same thing. So that's why we get this p by p plus. So this is these two are again homework. And one more trivial case is what? P plus q equal to 2. That means every time it is p equal to 2, 1, q equal to 1, so it change. So in that case, again exercise, find this probability of when p plus q is 1, find this. P plus q is 2. So p, q both are 1. So it is now easy. P, q, you can just put p equal to 1, q equal to 1. If p plus q equal to 2, then it means p equal to 1, q equal to 1. Just replace p equal to 1 q equal to, you can easily find what happened. You can easily find probability of x equal to 0 and probability of xn equal to 1. So this is easy case. So we assume from now, we assume that p plus q is from 0 to 2. That is 1 minus this mod of this is less than 1. And in that case, the limiting, what is the limiting distribution? The limiting n tends to infinity, your limiting distribution will be, so this is 1 minus p minus q is between -1 to 1, so that limit is goes to 0. So you know this is goes to 0, 1 minus p minus q whole to the power n will be go to 0 as 1 minus p minus q a minus lies between -1 and 1. So you know that as n to infinity, if mod r is 0 less than 1, this r to the power n is 0. So this part is 0. So we will get this is q by p plus q and limit n tends to infinity. Probability of xn equal to 1 is p by p. Obviously, sum will be adding will be 1, and that is 1. Now there is a question of the other way. If I give you a initial distribution and we have some PQ, can we find a Markov chain with this state space? And this will be the next class. So for today class, up to this.